Okay, yeah, so last time we just finished talking about the chain rule. Second derivative chain rule has some interesting little considerations to it. Mostly dealt with, though, by just realizing it when you take a partial derivative, add it to the diagram, and then always interpret appropriately in your algebra from the diagram. Okay, all right. So with that said, going on now, the implicit function theorem is part of the same section, in fact. You could, depending on how you look at it, you can think of it as a separate subject, but it is going to make significant use of the chain rule, so it's not unreasonable. Anyway, here we go. The first question that we're going to consider is, suppose you have a level set of a function of two variables. So an equation, right, involving two variables. Can you choose, and I emphasize choose, to view y as a function of x? And so let me point out why is it important that I talk about this being a choice? Answer, because that's certainly not how it was given, right? The way y is given, it's an input variable. F is a function of two independent input variables, x and y. Now I'm saying I would like to take this, what is given as an input variable, and I would like to view it as being an output variable, right? It is not at all clear that this can be done. For example, here's some easy examples. Let's suppose that your curve described by your equation looks like that. Right? Well, at this point here, or frankly, most of the points on this curve, yeah, sure. At least locally. So locally, in other words, if I ignore most of the curve, right, just ignore most of it, and say just near that point, I look at some little bitty piece of the curve there. Well, yeah, locally that passes the vertical line test, no problem. And so y is a function of x locally at that point. Okay. But notice not so everywhere. And so here's an example of a point where it is not true. That point right there. I don't care how locally you view it. Right? I don't care how myopic your view is. However little of the curve you look at here. However little. Notice the curve is at that point, at that instant that the curve gets to that point, it is in the process of what I like to call wrapping under itself. And so you're going to fail the vertical line test no matter what you do. So y simply is not a function of x there. And to be honest, it's not even close. It's not like it's, it would have been except for, there's a failure just at that one sort of point. No, I mean, if you're talking about at that, near that point, namely, if you have to include that point, then however little else you have to include, the whole thing, it's just not a graph of a function at all. Right? Yes?
So if you move the point up like ever so slightly.
Ever so slightly, then it's fine. Yeah. If you want to move up, and of course there's only so much resolution we have here, so let's say you move up to there, right? Then yeah, fine and dandy, no problem. Just be careful when you, here let me zoom in so I can do this a little bit more confidently. Just make sure that when you pick how much of the curve you're going to pick, don't go near the danger zone there, right? I mean, so you go to, take this little piece of curve, and now everything's fine again. No problem. Yeah. But at this point, bad. Okay, who cares? Right? What does this have to do with anything? Well, I'd like to flash you back real quick, and quicker than I'd like, sadly, but anyway, back to single variable calculus, where I know y'all have all done the following before. You were given equations like x squared plus y squared is equal to 1 and asked to find dy dx. And so what you're told to do is let's take the derivative of this whole thing with respect to x, right? And so they'll write something like this. And then you get 2x plus, and then let's see, now we have a chain rule problem because y squared is a function of y and y is a function of x. And so we'll write 2y dy dx equals 0, and then you can solve for the dy dx that you want. And huge problem. with what gets written down there. This is terribly problematic. Because I just took what is in fact given as one of two input variables, x and y, right? I took y specifically, that's an input variable, and I said, you know what, I'm just going to choose to view that as being a function of x. Like I can just decide that I would like to, and therefore it is. So, I mean, what if this was the point we were looking at, right? Then this is complete garbage, complete nonsense. It's wrong, like, and not just a little wrong. It's like dramatically face plant explosion wrong, right? So that's a problem. Now, some people deal with this. A lot of high school courses will deal with this by saying, "Oh, well, if this problem if this actually were a problem, then that would reveal itself further down the calculation when you actually plug in the numbers." And first of all, I've not seen a proof of that, and so I'm not 100% sure that that actually is true, that will happen every time. So that seems to me to be a leap of faith. Even if that were the case, I want to point out, and this is kind of a philosophical point, but look, y'all are in a math class here, so you're going to hear a math point of view. When we write down math, make sure you understand what we're actually doing here. We are saying, when we write stuff like this down, that this implies that. That's what you're doing. You're saying that if this is true, then this must be true. That's deductive reasoning. That's math. And it just does not follow, right? This just isn't a legitimate piece of deductive reasoning. And the fact that the illegitimacy may or may not reveal itself later is little consolation to the fact that that's non-mathematical garbage. Okay, so anyway, this is why we care, and so I want to show you how to deal with this, and I'm not going to deal with this as rigorously as would be ideal. It's just beyond the scope of this course. So what I am going to do, though, is show you I think a good little bit of geometric intuition that gets at the problem, I think, pretty satisfyingly, and then allows us also to get to what, in fact, the true punchline really is. So let's do that. And it goes like this. Let's suppose we had a problem, right? Let's suppose the curve really were in the process of wrapping under itself, right? That's this is the kind of problem that would lead to failure of the vertical line test. Therefore, by the way, here's the other failure: swing and a miss, right? So, so that's sort of vacuously. Anyway, that sort of a problem, the curve wrapping under itself. Well, that means at that point, I mean, if you think about how stuff wraps under itself, at that point, then it must have a vertical tangent line. Okay, so what? Well, here's the thing about that. If it has a vertical tangent line, then it has a vertical tangent vector. And I'm going to do two things with this tangent vector, which I'm going to draw over here. Now, by the way, same vector. There you go, vertical tangent vector. Two things to keep in mind about this little story of I have this curve and there's a tangent vector which is vertical. One point of view on that is, look, I am in fact on this curve, which is where f is a constant. That was the whole point to this. F of x comma y is some constant. Those are given. Right? 0. It doesn't matter. Any constant's fine. So that means f is not changing as I move along that curve. It's constant as I move along that curve. But here's the thing. As I move along that curve, at the point in question, as I move along that curve, I am moving with that velocity vector, that vertical velocity vector. And wait a second, vertical means I'm moving in the y direction. So what we've got here is a point that indicates, I mean, by what we know about this scenario, when I'm at that point, the function is not changing as I move in the y direction. And we have a real easy way to write that down. If the function's not changing as you move in the y direction, then the y partial is equal to 0. Okay, now again, so what? That doesn't, I mean, how does this, we were looking for how can I decide if I can view y as a function, and this does not explicitly give it to us. Yes?
Wait, why is it not moving in the y direction?
Why, what now?
I don't understand how. Isn't it moving in the y direction?
So this is moving in the y direction, right? And the function's not changing because at that point, moving in the y direction means I am in fact moving along the curve. Certainly moving along the curve means you're moving in the y direction because you have a vertical tangent line. Yeah. Okay, so this does not answer our question, but what we're going to do is we're going to pull a little math trick here. It's a very valuable trick. It's called the contrapositive. I'm a big believer. Hope y'all all make use of this whenever you can. It's very powerful. So the idea is that if, I'll write this down, if P implies Q, then it's equivalent to say, I'm going to run out of space here, but not Q implies not P. Right? It's just a fact of logic. P implies Q. You can make up any sort of little stories. Let's say P is if it rains today, and Q is I'm going to get wet. Right? And you can play through the game. P implies Q says if it rains, I'm going to get wet. The contrapositive here says if I don't get wet, then it must not have rained. It's the same statement, just kind of, it's almost like it's just a grammatically awkward version of the same statement, right? Okay, so we're going to pull that little trick here. What we have concluded already with this little reasoning is that if I have a problem here, let me label this here as a problem. If I have a problem, that's what this is. If I have a problem, then the y partial is equal to 0. The contrapositive then is if the y partial is not 0, then there's no problem. Right? And so this is what we were looking for. We were looking for a way to confirm that we have no problem. And here it is. Just take the partial with respect to y, confirm that it's not 0, observe that therefore, yes, I can view y as a function of x, and then go ahead and do this. It's totally fine at that point. Yes.
How could you logically explain why that is true? Just because it's df dy is 0, why does that mean you can't? Why would that imply that you can't?
Well, it's this whole reasoning that we just went through here. It's a multiple step argument. I mean, it's the contrapositive of.
Is there another connection you can make logically between a function and then df dy instead of using going through? Is there another way to understand this?
I mean, there's a much deeper way to understand it that we can't go through, more rigorous. I think this is the most satisfying way. I mean, in some sense, I did kind of a roundabout thing. I started by assuming there was a problem, and then I played a logic game, right? But this is the most satisfying way that I'm aware of. Yeah.
Does this only work for D with y partials?
No, this works for any variable as it turns out. I mean, I just drew the pictures for the x, but in here, if you want to view hypothetically x as a function of y, then you'd draw an analogous picture and you'd end up taking the partial with respect to x. Whichever variable you want to view as being a function.
Would you have a problem if it was the x partial equal to 0 because it still passes the horizontal line test? It's like a horizontal tangent line.
The analogous would be the argument would be analogous here. I mean, I don't want to go through the whole argument because we're short on time.
Yeah.
But there would be an analogous argument, and if the x partial were 0, then you would not be able to conclude that there's not a problem. Now, I emphasize that does not mean there would be a problem. I would just mean that we cannot conclude that there isn't.
Okay.
Yeah. So this is not a perfect test, but it's a one-sided perfect. It's not a completely perfect. Yeah. Okay. So that fixes this problem. This is a great, big, ugly gap in how high school calculus is often taught, and so we've filled that in now. If you think about it, this really is kind of a single variable calculus issue in a way, because look, it helps us do single variable calculus. Although we are using multivariable tools to make sense out of it, right? But now here's a truly multivariable version of it. This is a kind of a three-dimensional version, and I'm going to kind of, go through I'm going to go a little bit quickly through the analogous argument. Look, if you've got an equation involving three variables, right? So generically, you would expect that to be a surface like that. And you want to ask, okay, this surface that you've got there is, at a certain point on that surface, can I view, let's say, z maybe as being a function of x and y, right? Or, does the surface do something like this, where at a certain point, the surface is wrapping under itself, like I've got drawn here. You take this point, you take this point right here. Surface is in the process of wrapping under itself, and I don't care how little of that surface you pick, it's going to fail the vertical line test, and you cannot, at that point, or I should say near that point, you simply cannot view z as being a function of x and y. Right? So, we argue analogously. The problem, if there is a problem, right, such as we see there, if there's a problem, the surface is wrapping under itself. That means it's got a vertical tangent plane. Vertical means it's parallel to the z-axis. That means that as I move along the surface, right, this surface with that equation where f is constant, at that point there's a lot of different ways that I can go, but one of them is vertical, aka parallel to the z-axis, aka in the z direction.
So you just drew the vertical plane, or the tangent plane, right?
Yeah,
there.
yeah, right. So presumably this is at a point where the surface is wrapping under itself, and analogous to how we argued on the previous page, if you are in fact moving along a level set as you move in the z direction, that means f isn't changing, and you're moving in the z direction, so that means effectively a z partial has to be 0. And again, problem implies that's 0. Contrapositive says if that's not 0, no problem. Okay. All right. So here's a general version of the theorem. However many variables you're talking about, in variables, right? x1 through xn. If you have an equation involving in variables, and again, notice very importantly, we need to be able to view this as being something that's constant, and so you need to have your equation written with all the variables on one side, and then either 0 or at most some constant over on the right hand side. Constant is really the key point. So some expression equals 0. If the partial with respect to one of those variables is not 0, then you can view that variable as being a function of the others. Whichever variable you choose to take the partial and can confirm that you get not 0, you can choose to view that as being a function. And, go ahead. It's fine and dandy, no problem. Okay. So, yes.
So our definition of vertical keeps changing.
Sorry?
Our definition of the term vertical keeps changing. Like in this case, wouldn't it be along the xi-axis?
I didn't use the word vertical here.
Yeah, but if you had to take a vertical line test with this...
Then, but you don't take if it's not a vertical axis, then you don't take a vertical line test. You take a corresponding test appropriate to the axis. Yeah, no, vertical is a term that means in the context of 3 dimensions, in a situation where there's a well-defined notion of up, it means up. Yeah, right, yeah. Okay, so now here's a harder question. How do you take a derivative then correspondingly? So for example, let's suppose that I have decided that I can view xi as a function of the other variables, per this test. Right? I'm viewing xi as a function of the other variables. Hey, it's a function. Cool. You know what you can do with functions? You can take their partial derivatives with respect to their input variables. Okay, so if xi is a function of these other variables, right? How do I take a partial with respect to, for example, xj? Okay. All right. So you can write down a bunch of algebra to do this, and I'll go to the algebra in just a second, but I want to start with a picture. And specifically, now let me mark up my picture here a little bit. I want to erase this little arrow here just for a couple of minutes while we argue something in advance. So, first thing I want to observe, I have already decided that I can view xi as being a function of the other variables. So let's get that onto our picture. I mean, if in fact we're viewing xi as being a function of the other variables, well, let's indicate it so. All right, so here they are. The variables are x1, x2, etc., etc. Now, not xi, right? The whole point is we're viewing xi as a function of the other variables, so not xi. So big gap there, etc., etc. I'm going to put xj here because I'm going to need to talk about it, but it's just another one of these variables all the way out to xn. Okay. All right. Now, what I'm going to do, no particularly obvious reason why, but seems like maybe a little bit relevant. I'm going to take this function f that we know is a constant, and I'm going to take its partial derivative with respect to xj. Strategic thought. Why am I taking its partial with respect to xj? Well, I mean, look, I eventually am going to want to know a partial of something with respect to xj. So, I don't know, seems like a reasonable thing to try. Even though I'm not taking the partial of the thing that I really want, I want the partial of xi. I'm taking the partial of f. It's not really what I want, but who knows? Maybe we'll get lucky, right? So let's do that. And how do we take the partial of this f with respect to xj? And, well, of course, we use the chain rule. And we write down a bunch of terms that correspond to a bunch of different paths, a bunch of different intermediate variables, etc. Right? Okay. Here's the thing, though. Very importantly, we're taking a partial derivative with respect to xj. Right? So partial derivative means that we're actually going to be holding all of these other input variables constant. I'm going to hold all these variables constant except for xj. Okay, well, so that means, look, x1 is a constant, x2 is a constant, x3 is a constant, et cetera, et cetera. This isn't an input variable. We're going to hold that constant and that constant and that constant. Now, wait a second. Now, not xj. We're taking a partial with respect to xj. That's a variable. We keep that a variable, but then everything after that, all constants. Right. Okay, so those are all constants, but wait a second. That means, likewise, I mean, that's all these things are up here. Those are all constants. So when I talk about all these different paths that through which changes can propagate, like that, when I change xj, how much does that cause x1 to change? Well, nothing, because x1 is constant. I'm holding x1 constant for the purpose of that partial. So that term's 0. And likewise for the vast majority of the remaining terms. And there's only 2 terms that aren't 0 by this exact same fact. Those 2 terms are that one that goes by way of xi and that one that goes by way of xj. And that gives us the following 2 terms. Here, let me color code those better. That green one is that term. That blue one, I'm going to say, is that term. Let's not lose sight of the fact that f is, in fact, a constant. So this derivative altogether, of course, actually is 0. Now, what happened with that blue pathway? How can I just say that that's... where's the other factor? Shouldn't there be a... in some sense, I only put that part of the path on there. What happened to this part of the path? Well, of course, if you think about it, that says partial of xj with respect to xj, and that's an easy one. Right? When you change xj, how much does xj change? Well, same amount. Right? So that factors 1. So that's the breakdown. I mean, this I think is a very satisfying way to think about it. Here we've applied the chain rule to how f changes as xj changes, understanding xi as being a function of all these other variables. And this is the total picture. This is what happens. And now you can just solve for what you want, right? So going back to the, let's see here. Yeah. Going back up to here, what is it that I wanted in the first place? I wanted partial of xi with respect to xj. Check it out. There it is. Right? That arrow that I wanted to know, that partial derivative. It's part of that little bit of algebra, so you solve for it, and there you are. So there's your handy-dandy equation for how to compute that partial derivative. There is something very unsatisfying about the result that we get there. A lot of students are freaked out by this. A lot of students specifically are freaked out by that minus sign because a lot of students think, but it just feels like, I mean, come on, aren't these two df's, aren't they supposed to like cancel or something? And then the xi's and the denominator of the denominator becomes it just all kind of should work out, it seems. And that minus sign seems wrong. And this is wildly misled. That's not a thing. So this, here, let me zoom so I can focus better. This thing that looks like a fraction, it's not that simple. It's not like partial f is a well-defined single thing that lives by itself that I can just give a name to and toss around like it means something. It just isn't. So don't treat it that way, please. It's very important. It's going to lead you to big problems if you do. Likewise, again, that thing there, it's not a thing by itself. This notation that we write like a fraction, we write it like a fraction because in some situations, under certain key assumptions, very narrow, specific assumptions that only apply sometimes, it behaves kind of like a fraction in those cases, right? But it's not actually a fraction, and you cannot just treat it like that. If you'd like to know, okay, well then how can I think about that? I mean, where's the intuition for this? It just seems really morally wrong with the whole minus sign and all. So where's the satisfaction in that? And that comes from, I think, the fact that we are dealing with what is in fact a constant. Right? We are not, as we do this calculation, trying to understand how much f is changing. We go into this calculation already knowing how much f is changing. It's not. Right? So think of it like this. Think of it as the amount that f would be caused to change by that propagation has to cancel with the amount that f would otherwise be changed just by that propagation. They have to add up to 0. These aren't things that add together. These are things that cancel each other. Because after all, f is not changing. So I think I find that satisfying. Hopefully that might give you some satisfaction as well. Okay. All right. So now, with the picture, the argument been made, let me show you the what I think is a simpler way to think of this picture. This is what I had before. All this stuff that we had down here was mostly just a way to justify that what we were thinking of, which is all these other variables are constants. And there's two ways that changes from xj can propagate. On the one hand, they can cause xi to change, which causes f to change. On the other hand, they can go directly. And so you can, in some sense, write down this algebra here. That algebra you can write down just directly from that picture, which, another way a more compact way to think about it. But anyway, it's just an option. Okay, so here is in practice how y'all are going to do these kinds of problems. So here's a little bit of algebra. Suppose we know this algebra. What's the partial of x with respect to z at a given point? Well, wait a second. And by the way, this is a very serious point. This is a very grading intense point that I'm about to give you. If the question says, what is a derivative of the variable x? Notice that the subtext of the question there is, apparently we're supposed to view x as being a function. Again, the only things you can take derivatives of are functions. You can't take derivatives of bicycles. Right? So x, I emphasize, is not given as being a function. You cannot just assume that it is a function. Very often it is not a function. So step number 1, we're going to have to view x as being a function. We're going to have to establish that we can, in fact, do that. And only after establishing that x is actually a function can we go on to talking about its derivatives. Okay. So step 1, implicit function theorem. First thing we talked about today. If you want to view x as being a function, you got to take the partial of f with respect to x, the variable that you want to view as a function. Okay, so a little bit of algebra. There's that partial derivative at the point in question. 1, 2, 3. The value is 4, which is not 0. So yes, I can view x as being a function. We're good. Is everybody good with the first half of the problem there? Okay. I emphasize you have to do this. It is completely unacceptable if you skip straight down to the formula here and just plug and chug away, assuming, stuff like that works out. Wrong. False. And again, I further emphasize, you may have some consolation in the fact that even skipping that point, you will get to the correct number at the bottom of the page. I remind you, I emphasize as much as I possibly can, it's not about that, right? This is not a class about numbers at the end of the bottom of the page. This is a class about reasoning, right? So you've got to give me proper reasoning, and if you do just this, your reasoning is grossly incomplete. And it'll be graded accordingly. Just a heads up, FYI. Okay, so we do the calculation here. We establish that yes, this is indeed a function, and with that done, then it's a matter of compute away, knock yourself out. Here's the formula, right? Adapted from the previous page, and there's just some calculations in there. Partial derivatives. This partial derivative is that. This partial derivative is that. And plug in at the point in question. Keep in mind we're talking about at the point 1, 2, 3. So at the point 1, 2, 3, plug in those numbers into there, and there's your answer. It's very pluggy-chuggy after that. Okay. All righty. Okay, so I emphasize, make sure to, it's so important. Probably about half of the points on the question. Ballpark, to actually address whether the thing you've been asked to compute the derivative of actually is a function. Okay. And one last comment, and then we'll go on to the next thing. We're trying to make up for lost time here. This might not even be stated. It might just say, here's a point, and we're going to be, or here's a surface, and we're going to be looking near that specific point on this surface. What's that partial derivative? If the question is stated like that, you are still responsible. You've got to go through this argument and confirm that, yes, indeed, that actually is a function before you start just taking derivative. It remains, in other words, that you still don't know that that thing is a function, and so you still have to do that. All right, that's enough emphasis on that. All right, so moving along. So the next section, directional derivatives. A quick reminder, here's our some old formulas that we've seen before. Now, where have we seen these before? Different contexts, I suppose. You could say we saw this formula in the section on linear approximations, maybe. But I like to think of this formula, very, very similar looking, right? That is something we saw in the section on the chain rule. This is our chain rule for when the fundamental input variables are there's only one of them. Okay. All right. Now we're going to consider a special case of this formula. to develop a key concept, we're going to consider the special case where we're looking at a real valued function, right? So real valued just means that the values of the function are just real numbers, a single real number. So real valued is a convenient way to say the target is R1. Okay, and if you think about it, if there's only one output value, then that means there's only one row in the Jacobian matrix. And then if you sort of put that and that together, we have here only one row, and this velocity vector has, it's just one column, then really we're doing a dot product, right? This is, in fact, just a dot product. And in fact, if you look at what this single row is made up out of, it's the gradient. It's the vector of partial derivatives. So if only from an algebraic sort of like computed up standpoint, here's what the chain rule turns into, right, in a real valued sense. Real valued function. Okay. So fine. So neat fact, dot product with the gradient has this lovely feature that it turns input changes into output changes. Of course, that's our big perspective on what derivatives are. Derivatives are relationships between input changes and output changes. Okay. All right. Okay. So, so let me color code, by the way, here on the picture. The gradient vector. That's the thing that you dot with input changes to get the corresponding output changes. All right, so we're going to be looking at a special case of this scenario. It has some nice applications. The special case that we're going to be looking at is if the input change that I did in yellow, the input change is a unit vector. So we're going to see over the next few pages why that's an interesting special case. But anyway, for the moment, we're going to consider just the special case when the input change has to be a unit vector. I emphasize not because you are sort of morally obliged to. I'm saying this is an interesting special case. In general, these formulas work for any input vector. Right? I mean, the chain rule is very powerful. It's very useful. Right? Okay. So this book makes the choice to call this result when the input change is a unit vector, and the corresponding output change, namely the df dt or the df, computed as a dot product with a gradient, this output vector is called the directional derivative. That's the term people like to use. Okay. Now, let me tell you why people like this term directional derivative, and there's some naturality to this. Well, we're trying to keep track of how fast the function's changing. You might say as we're moving in a certain direction, right? After all, if this is a unit vector, what better way to describe a direction? Not a direction and a magnitude, but if I want to explain just a direction, well, look, a great way to describe a direction is with a little arrow, right? With a vector. But vectors have directions and magnitude. Okay, but I want to talk about just the direction. So what's the most sort of canonical, ignorable magnitude that I could attach to a direction, right, to give me a vector that I can actually write down and do business with? And one is a pretty natural choice. Right? So a unit vector is very often used as a tool for describing just a direction for that reason. And so you could say here what we're doing is we're taking a derivative. I want to know how fast the function is changing as I move in a certain direction, the direction being described by a unit vector. Okay, so thus the term directional derivative. Okay. Now that being said, here's a little cultural observation, and this is a frustrating thing, but unfortunately, it seems not everyone agrees on what this word directional derivative should mean. And to be totally honest, I'm kind of in the other camp personally, right? So, after all, if you look at this formula, something computed as dot product with the gradient, well, we already know that that works for any input vector. Why should I restrict my use of this lovely formula, dot product with the gradient? Why should I restrict my attention to its unit vectors? This works for any vector, right? So there are contexts, heads up, just be aware, right? There are contexts outside of Math 212 where the term directional derivative will be applied even if the input vector is not a unit vector. And so what you have to do is you just have to be heads up on that, just head on a swivel, right? It's always, if you hear the term directional derivative, you should have this instinctive sort of like flinch. Oh gosh, which one does he mean? Does this writer mean unit vector velocity, or are they just using sort of a general term for the chain rule? And just look for the context and identify appropriately and interpret accordingly. So anyway, like I say, heads up. Okay. We, in this course, will be using the same choice that the book does. The book chooses that this must be a unit vector. So in the context of Math 212, in this course, directional derivative means that this vector here is a unit vector. Okay. Outside of Math 212. Different with every book or writer or collaborator or whatever. Okay, all right, enough of that. The notation, by the way, the notation, just got to be heads up about this. It actually is pretty reasonable notation. Capital D for, I don't know if it's directional or for derivative. Both, maybe. Anyway, D for directional derivative. The vector that is your direction that you're going, make that a subscript. And this is a way of saying, look, this is a kind of derivative that I'm taking of this function f at this point A. And so the rest of the notation makes loads of sense, right? I'm doing this to that function at that point. Okay, very familiar. All right. Okay, so different ways to think about it. The first observation I want to make is that we already made this observation, but it's a special case of the chain rule, right? The chain rule says dot product with the gradient makes sense for any vector. Here we're saying, yeah, but we're going to look at the special case of where the input velocity is a unit vector. So it's literally a special case of the chain rule, for whatever that's worth. And I like to make this other observation. It's a generalization of the idea of a partial derivative, right? Notice, if you use a standard basis vector, that's a unit vector. If you use a standard basis vector as your unit vector, compute the dot product with the gradient with that standard basis vector, and see how this dot product works out. Right, most of those terms are zero, and what you end up with is literally the corresponding coordinate of that gradient. Namely, you get the corresponding partial derivative. So partial derivatives are special cases of directional derivatives. Directional derivatives are special cases of the chain rule point of view. Okay, so geometrically you might think of it like this. If your input velocity is a standard basis vector, then you're doing a partial derivative. If it's a unit vector, but not necessarily a standard basis vector, now you're doing directional derivatives. And if it's just, oh gosh, who knows what, just any random vector, then, well, it's certainly not a partial derivative, and in this context, this book's context, it's not a directional derivative, but you are still taking a derivative as you would compute with the chain rule. Okay, all right. Okay, so some neat properties I want to talk about. It turns out, and this is really nice, this is one of the big ones, a directional derivative, you can think of it as computing how much the function changes per unit distance traveled in the direction that you're going. That's a very natural thing to want to talk about, right? Maybe I'm walking along in the woods, and I've got some function I've got an app on my phone or something, and I've got the raw data, and it's going to tell me, my directional derivative of temperature as a function of, as I walk, right? Well, I would like to know for every mile that I walk, how much is the temperature going to change? That's a very reasonable thing to want to know, right? And you could say, why not compute the rate of change of temperature with respect to time? And you could say that, but I could also not want to deal with that. I don't want to have to, I'm going to assume I'm walking with a certain speed, and then now I got to stick with that? I don't really want to stick to it. I want to walk at a leisurely pace. I'm out for a fun stroll. I would like to be able to stop occasionally and look at the scenic overlook before I go on and not have to keep up with my pace, otherwise my derivative calculation's wrong. Right? I would just like to know, look, for every mile that I walk, the temperature goes up 1.3 degrees. And know that that's a true fact, independent of how I walk. Okay. So, very natural thing. Okay, so how do we know this is true? It's easy to get to this conclusion. dx dt is a velocity, of course. Velocity you can think of as being a speed, aka a magnitude, times a direction that you're going. Right, here you go. So you've got a unit vector describing the direction that you're going, and then the speed is, the magnitude, the speed at which you're going in that direction, and altogether, the velocity is that product. So just very common to want to break down velocities as unit vector direction times speed magnitude. Okay. So let's take that formula and do something real algebraically simple to it. I'm going to take this formula right here that we just wrote down, and I'm going to just dot both sides with the gradient vector. That's all I'm doing there is dotting both sides with the gradient vector. And check out what we get. I don't want to give away the next thing. The chain rule tells me that gradient dot velocity gives me df dt. That's old news from last week. I know that velocity is the rate of change of position. That's ds dt. S being, how far have I walked. So ds dt is my speed. Right? So the thing is, and let me scratch this out for a second here. This equation down here is going to be a true equation if the left side is df dt, and if the factor on the right is ds dt, then unavoidably, whatever I end up with here, it had better be df ds, right? That's just kind of what you need to make the single variable chain rule actually work, right? That's single variable chain rule because I'm viewing the function as I'm viewing f, whatever that is, as a function of position, and position as a function of time. That's all single variable, right? So therefore, this thing, that directional derivative, has to be df ds, as we were hoping. So nothing to it. Okay, neat fact. Valuable interpretation of directional derivatives. Let's take that same scenario and think about it in the graph context. So, by the way, maybe when we're hiking, maybe I'm not interested in temperature as a function of distance traveled. Maybe I'm interested in altitude as a function of distance traveled. Altitude, that's the thing. If you're looking at a graph of a function, you're thinking of the function as representing altitude in some sense, right? So, knowing that the directional derivative is df ds, well, look, as I'm going in this direction, if there's a unit vector representing my velocity, then I know I'm traveling in a plane like that, and that therefore, as I hike along the mountain, that's the curve that I'm moving on, which means that I have a tangent line that I'm moving along, and that tangent line, you can see it right here on the picture. There's df, right? That's how much over a short little distance. That's my linear approximation of how much my altitude changes. And here's my ds. That's, over a short little, as I walk, along the map anyway, how much distance have I traveled? So you can see it right there that interpreting interpreting the directional derivative as df ds literally gives me that the directional derivative is the slope. It's the slope of the side of the mountain as I'm hiking. It's the slope of the graph of the function that I'm looking at, whichever you prefer. Yeah. How are we doing on that? Is everybody good? Questions? Yep.
Do all these tests hold true even in a polar coordinate plane?
Oh, no. This is all strictly rectangular.
Only for x, y.
Strictly rectangular. Yep. Absolutely. Okay. Alrighty. So couple of quick examples. Let's see how we're doing on time. No, I'm sorry. We're already over time. Sorry about that. Okay. Good stopping point for today. See y'all later.